Okay, your next homework assignment's due on Tuesday in class, and then also the calculations for Lab 3 are going to be due during lab. We'll switch the lab groups that day so that the people who started at 3 o'clock last time will meet at 2 and vice versa. I've got your graded lab reports here. I'll hand them back as you're working an example today. A couple of comments about the labs. Just as a reminder that in technical writing, it's customary, for whatever reason, to avoid the use of the first person. And so you don't say things like I, or we, or our, or my. I think that probably the reason why that's the custom in technical writing is to try and take the scientist out of the story. You know, the report is about the experiment, it's about the data, and it's not about you or what you did. It's about what was done to the sample, and so avoid the first person, as it's called, any reference to yourself or other people. Also avoid subjective characterizations like a statement like the correlation between predicted and actual values was pretty close. Don't say that it was pretty close unless you've run the experiment so many times and you have sort of a history of what would constitute a close agreement and what would constitute a wide agreement. And really, it would be only up to somebody who's an expert at a particular experiment or test to say whether the results are good or bad. So don't make any subjective reference to how the results turned out. Just leave it at what the percent error was. You know, it was 40% error, and you don't know really if that's good or bad necessarily. You know, besides that, I felt like the reports were good. It was pretty clear to get the information that was required. I noticed that some of you typed your calculations in Microsoft Word, and that ends up looking pretty good if you put the time into it, but I think that it's really a lot of work to get the superscripts formatted correctly and insert the symbols and the equations. And so as far as performing the calculations, I'm happy to see them done on engineering paper neatly, and that's good enough for me. You don't have to type the calculations into the Word document that you prepare necessarily, because I know that can be a lot of extra work. So just a couple of comments about the lab reports, and I've put some specific notes in them. The grades are entered into MU Online, and so if at any point you want to check and see what your score is so far in the course, you can go to MU Online, and it should be up to date, including the homework assignment that you submitted on Tuesday that I'm going to return to you today. So any questions about labs or about these announcements before we move on to talk about manometers? Okay. From time to time, I'll have students ask questions that I don't know the answer to. And when that comes up, I try and do a little bit of research, and I'll put a slide into my presentation that addresses the topic they brought up. And 2 semesters ago, so it was 2 years ago when I taught this class, someone asked whether the pressure changes the freezing point of water. So if water is in a really high pressure environment, does that change its freezing point, or if it's in a low pressure environment? So the answer to that is it doesn't change the freezing point of water unless the pressure is below 1 kilopascal or above 10 megapascal. And there's a phase diagram that shows that relationship, and on the phase diagram it shows that the boundary between a liquid and solid for water, so in other words, this boundary is the freezing point, is not changing at all. That's a constant freezing point over the range of about 1 kilopascal to 10 megapascals, and then it deviates ever so slightly. It looks like the freezing point is becoming depressed as the pressure goes up. And then it changes pretty crazy when the pressures get very, very high. But over the range of temperatures and pressures that we're likely to encounter under ordinary circumstances, we can assume that the pressure is constant, that the freezing point is constant with respect to pressure. And you'll notice, by the way, that that was 0 degrees Celsius that was the freezing point. And so it actually is a little bit lower as the pressure increases. And then things get crazy. Another question that came up in a previous semester was, what's the temperature dependence of the bulk modulus of water? Remember, bulk modulus is the relationship between pressure change and volume change. And so that is how compressible is water as a function of temperature, is essentially what the question was. Does water become more or less compressible as temperature changes? Now, the typical bulk modulus of elasticity for water is 2.2 times 10 to the 9th pascals. Now, compressibility is the inverse of bulk modulus. And so if we switch what's in the numerator and the denominator for bulk modulus, right now under bulk modulus, what's in the numerator is the dP. So that's the change in pressure. And then the specific change in volume is in the denominator. So if you flip that, then what that's called is compressibility. So if you're relating the change in volume relative to some unit change in pressure, that's compressibility. And the reason why I put it in those terms is I was able to find a diagram shown here that depicts the change in compressibility of water as a function of temperature. And it's not an enormous change. This is a pretty flat curve. But what it shows is that water is slightly, its compressibility changes slightly over the range of temperatures, but again, that's pretty moderate. Over the range of typical values that you'd see in a normal environment, maybe from 0 to 40 Celsius, it's the compressibility probably changes only 10% over that range. And it's still going to require a lot of pressure to have a minimal change in the volume that's occupied by a certain amount of water. So I thought that those were interesting questions. Hopefully you'll have some interesting questions. I'm not asking you to try and stump me necessarily. But if something comes up that I don't know the answer to, then I'll always do my best to find the answer if I can. Oh, by the way, I think the reason why, as I read into it a little bit further, the reason why temperature effects have an impact on compressibility is that, of course, water is H2O. Regardless of the temperature, water remains H2O. But as the temperature changes and as these molecules have different levels of kinetic energy, they're moving around and vibrating based on what the temperature is, they have these different characteristic orientations. There will be certain groups of molecules that orient themselves together, and so these clusters change based on how much kinetic energy the molecule has. And these different clusters of water are progressively more or less compressible. And so it's not that the individual single water molecule changes so much as that the bound groups of water shift over the range of temperature. All right, so today we're talking about YouTube, not the video channel YouTube. This phrase YouTube manometer has been used for a really long time. It greatly exceeds the existence of YouTube, the website. It's called the YouTube because it's in the shape of a U. And who can remember what the problem with the case in a previous lecture we talked about? If you have a pressurized pipe and water's flowing through the pipe and you fracture the pipe so water's spraying out all over the place, and then what if instead of doing that we put a tube in it and the tube goes up really high and then we measure the pressure in the pipe by letting the water level go to that high. What's the name of that when we put that in there? Piezometer. Right, good. So this piezometer is a way of measuring pressure. But what's the weakness of a piezometer? I talked about in the previous lecture the disadvantages of using this to try and measure pressure in a pipe. Be very tall, right. We'd have to walk around on stilts because a typical water network of 500 kPa would mean that the delta H is going to be about 50 meters. So not practical if that was going to be the way we'd measure pressure. And there's two other kind of bummers for using this as a pressure measurement tool. Open to the air, right, and that's actually where both of those other disadvantages come from. The first is that things could get in, contamination, the bird that flies over just the right time and it gets into the water network and all of a sudden everyone's got bird flu, you know. Or things could get out. And, you know, if it was water, it could evaporate water out, and that probably would be minor losses, but it would preclude this from this pipe from carrying gases, because if you had a gas and it was air, then the gas could just simply escape. Or if it was a volatile liquid, like natural gas, a gas that's under pressure and compressed, it could be dangerous. So things could get out, things could get in. A U-tube manometer overcomes all of those disadvantages. It prevents things from getting in and out quite so easily. But the main advantage that a U-tube manometer has is we don't have to have a 50-foot or a 50-meter delta H in order to measure typical pressures. Now you'll notice, let's just talk about what we've got here depicted as a pipe. The water is flowing through the pipe and it's pressurized, and it could either be above or below the pipe that this tap into the pipe occurs. That doesn't matter. It's showing here that it's below the pipe that it's matched in. And so this is water or oil, whatever's flowing through the pipe is in part of the U-tube, but then there's an interface here. And that interface is where two different liquids come together. And they're saying, and it's depicted as being a little bit darker blue. So that shading implies that it's a different liquid. But it's a manometer liquid, and what we can do is choose a liquid for this manometer fluid that is very dense. And if you choose a liquid that is very dense, then that means the delta H doesn't have to be as big. Because remember, what we've got between the opening to the U-tube manometer and down here to this level is a change in pressure. We can go different places and just apply the hydrostatic equation to find the pressure at any point in the system. But what we're using this manometer for is to measure pressure. So delta P is the objective of using a manometer, is to characterize what is delta P. And remember, from the hydrostatic equation, we calculate delta P is delta H times gamma. What do we call gamma? What's the name of this variable? Specific weight, or the unit weight, and what it has units of newtons per cubic meter, or it has units of pounds per cubic foot. It's related to the density of the fluid. Density times G gives us the unit weight. So in a U-tube manometer, we calculate the change in pressure by just applying the hydrostatic equation. So let's say we've got this system here. What's flowing through the pipe is water at 10 degrees Celsius, and we've got mercury as the manometer liquid. And we want to find what is the pressure at the center of the point, at the center of the pipe, using the hydrostatic equation. Well, it's very easy, and our strategy here is to start where we know the pressure. And where we know the pressure in this case is at location 1, because that pipe is open to the atmosphere at 1. All right? So what we can say is that the pressure at 1 is 0. Now, from that, you can already know that I'm working in terms of gauge. If I had said the pressure at 1 is 101 kilopascals, then you'd think, oh, he's working this problem in absolute terms. But I'm working in gauge pressure, and the fact that it said just find the pressure, whenever it doesn't specify gauge or absolute, it means gauge unless you're working a vapor pressure problem or if you're working a gas law problem. But if it just says find the pressure, then it means relative to atmosphere, so gauge pressure.
Is that plane underneath
Yeah, that's an L. And so it's talking about that distance between 3 and 4 is 183 centimeters. So what's the pressure at 4 is where we're working towards. The pressure at 1 is 0. What's the equation for pressure at 2? Delta H times gamma plus P1. So it's important that we add on the plus P1. Now, P1 in this case is 0, so we're not going to get into too much hot water by forgetting it in this step. But it's just good to be in the habit of saying it's some change plus whatever it was at the last location. So we're doing like a dot to dot, connecting 1 and 2. Starting at 1, the pressure at 1 plus the change between 1 and 2. So the pressure at location 2 is going to be 0.45 meters, and we're going through mercury. So what is the unit weight of mercury? In your book, I think it probably has the unit weights of various fluids. Has anybody got a textbook and can open up to the appendix? And I think probably it will have either the specific weight or the density of mercury. If not, I know what it is, but I'm just hoping that we can find it in the textbook. There it is, mercury. Got the density, specific gravity, specific weight. All right. So what's the specific weight that it says there? 133,000 newtons per cubic meter. Okay? And that's listing for 20 degrees Celsius. I've got a different unit weight that I must have looked up specifically for 10 degrees Celsius. I'll go with the one that I've got, but you can now see that that value is accessible in your appendix. I looked up that the unit weight of mercury was 133,416 newtons per cubic meter. So that's pretty close to the value of 133,000 that's in your book. A little bit more dense, I think, because of the cooler temperature, 10 degrees Celsius versus 20 degrees Celsius. So I'm going to put in 133,416 newtons per cubic meter plus P1, which was 0. That means that the pressure at 2 is 60,037 pascals. A pascal is the same as a Newton per meter squared. I think you see from this why they use mercury as a manometer fluid. It's a way of getting a big pressure change without having to have too much height. Since it's so dense, you get to have a lot of delta P for a very small delta H. You know, we'd have to have 13 times as much water to get the same pressure change as we got with mercury. Mercury has a specific gravity of 13.56, so that's why mercury is a common manometer fluid in problems like this. What's the pressure at 3? Same thing. Why is it the same? They're at the same elevation through the same fluid. That's true. So we can say that pressure 3 is equal to P2, which is 60,037 pascals. Now let me give you a caution. That logic we just used to find the pressure at 3, there's limits to that logic. The pressure at 2 and the pressure at 3 is the same because they're at the same elevation. But what about, okay, here's 1. Now what about this point right here? Okay, we've gone through 2 different fluids to get between 1 and 2, and so it's not going to be the same pressure at 1 as it is here. So don't fall victim of always assuming that, you know, if it's at the same elevation, it's the same pressure. It's only when you're going through a continuous fluid. And we did that. Between 1 and 2, they were connected by the manometer liquid. Okay, so I'm glad you noticed that quickly.
What if that 0.3 was a little bit higher or lower? We would still use the same formula, but...
If 0.3 was a bit higher or lower?
Yeah, same fluid, just a little bit higher or lower than 0.2.
Okay, so let's say that we had a point here. If we wanted to find the pressure here, then we just find out what's the vertical elevation difference between here and there, and we just use the hydrostatic equation.
Right, we're still using that equation right here. Our delta H is just 0.
That's right. Yeah. So, yeah, the reason why it's the same, we could say it's P2 plus delta H gamma Hg. You're absolutely right. The reason why P2 and P3 are equal is because the delta H is 0. That's the y of it. Very good. Last step, P4. Okay, what's the equation for that, P4? Pretty close. Why is it minus instead of plus? Why is it minus instead of plus? Okay, we're going up now. We were going down before. So when you go down, you're adding pressure. But then when you're going up through a liquid, you're losing pressure. And so that's why we're going to subtract whatever incremental difference in pressure there is between 2 and 3. So P3 is 60,037 newtons per meter squared minus 1.83 meters of water. 9810 newtons per meter cubed. Okay, and that difference works out to be 17,952 newtons per meter squared. So that the total pressure at 4, when we subtract that change from the 60,037 that we had before, is 42,085 pascals. So that is how we find the pressure at 4 going through a U-tube. Any questions about that? All right. So, what's the probable variation in a problem like this? Think in terms of, what if you were writing a quiz question? You're going to write a quiz question. You're going to try and test someone to see if they understand this. What are the different things, the different ways that you could ask a question like this? Okay. Okay, so you could make the delta H unknown. Like, you could give 2 known pressures, and then the unknown is find out what is delta H. Or you can have a given delta H, and then the unknown is one of the pressures. Or, we could also have L be unknown. So, in the hydrostatic equation where you've got delta P, delta H, and gamma, any one of these could be the unknown. In this problem, we were finding what is the pressure. We just talked about how you could give pressure and find delta H is the unknown. Or you could say, here's the pressure difference, here are the lengths, what's the fluid? You could have 3 or 4, if we make it a multiple choice question, have 3 or 4 fluids as the manometer liquid and say, what was it? Was it mercury? Was it oil? Was it ethylene glycol? Whatever. All right. Well, let's try a finding the pressure type problem. I'd like you to work this example either individually or with a partner, talk it over. we're going to find the pressure at A. This is a pipe, it's going into the page. There's some pipe, and at the center of the pipe, we want to find the pressure. And in this case, off the top of the pipe is a manometer that has all these twists and turns, and it seems really complicated, but it's just the hydrostatic equation. This is just accounting, plus and minus. You're adding pressure as you go down through the fluid. You're losing pressure as you go up through the fluid, applying the hydrostatic equation. Start where you know something and work towards the unknown. So we know the pressure at one location in the drawing, and we're going to work towards A from that location where we do know the pressure. All right? We're just applying the hydrostatic equation over and over and over, starting with at location 1. I set this to be location 1, up at the interface of the air and water. The pressure is 0. And then I go down to the interface of water and mercury. So at this location, I'm saying that the pressure is 8,829 pascals. And then I'm going down through 0.6 meters of fluid. So at that location, which on this set of solutions is referred to as P3, it is the pressure that there was at P2, 8829, plus 0.6 meters of mercury, which increases the pressure by 80,000 kilopascals. The total pressure at 3 is 88,879 pascals. The pressure here and there is the same. Pressure 4 is equal to pressure 3. And now what I need to do is go up to, from this location, up to here. And so the total distance between this interface and the next interface, the vertical elevation difference, is 1.8 meters. So I've found the pressure change from here at 4, I'm calling it, and 5 is this location. So it's whatever the pressure was at 4 minus 1.8 meters of oil that has a specific gravity of 0.8. And then the pressure here and here are the same, since it's same fluid, same elevation. And then going down, the pressure is increasing again. One last stretch, it's increasing 1.5 meters of water. So ultimately the pressure at A is 89,467 pascals. Yeah.
Can you go up to 0.3 to that line there and then do?
Sure. Yeah, you could have broken it up into from here to here and then from there to there, if you'd like. I combined that step, though, since it was the same fluid, just into a single step.
And do you always subtract the bigger number?
You subtract when you're going up through a fluid, and you add when you're going down through a fluid. And that's why...
Oh, okay, but you're using the previous pressure, then plus or minus the...
That's right, yeah. Don't let the dimensioning throw you off. Sometimes just the way the dimensions are drawn, it can make you feel like you're supposed to solve the problem a certain way, but the dimensions are just there to show you what different distances are, and so you can combine them together. Don't be forced into a box by the given information necessarily, or the way that the given information is formatted. Any other questions about this example? Another kind of manometer besides a U-tube manometer is what's known as a differential manometer. And so in a differential manometer, instead of having one end of the tube open to the atmosphere, that is connected back into the pipe again. And it's called the differential manometer because it measures a pressure difference. It's measuring the difference in pressure between location 1 and location 2. Now, it says right here that the fluid flow is from left to right because it shows you the arrow. But how is it that just by looking at this, you should know that the fluid flow is from left to right? How does this guide you towards that conclusion? The fact that it's lower on one side versus the other.
The lower side means that there's more pressure acting on the manometer.
All right, so you're saying that it's lower here, and that it means that there's more pressure since it's lower, and that's right. So why is that consistent with the flow being from left to right?
You would go from higher pressure to low pressure.
Liquid flows from low pressure towards high pressure. That's exactly right. Fluids flow from low to high pressure. So our atmosphere, for example, wind, if you've got low pressure over your town, air is going to be moving towards that low pressure front. Things flow from high energy to low energy. Water flows downhill, fluids flow towards low pressure. And so in this case, the fact that it's high pressure at 1 is what's forcing the liquid towards 2, is because it's a location where there's less pressure. Or another way you can think about it is just that the pressure is decreasing due to pipe friction. That's how energy loss is expressed in a flowing fluid. Energy is, as water flows through a pipe, because of the friction of that pipe, the pressure is decreasing. So any way you look at it, what the differential manometer is able to do is it's able to characterize what is the pressure difference between location 1 and 2. And the way that you calculate the pressure difference between 1 and 2 for this horizontal pipe, this is only in the case of a horizontal pipe, then the pressure difference is equal to the difference in the unit weights of the fluids. So if this was mercury as the manometer fluid and water flowing, you'd say mercury minus the fluid, the unit weight of water, multiplied by delta H. So the delta H would be measurable using a ruler or given in the problem statement. So then you could find out what's the difference in pressure between 1 and 2. And this is very similar to what we do in the lab. That pipe rack that's in the lab that I said is a little bit top heavy and it tips over easily. There are taps at 1 meter distances so that we can find out what's the pressure difference through different kinds of pipes. And we could use a differential manometer like this in order to find out what is the pressure difference. In a way, that would be more satisfying than the electronic instrument that we actually use to measure the pressure difference. It would be more fun if we had a differential manometer filled with mercury that we could play with. All right. So more generally, so if the pipe isn't horizontal, this is the equation that's always valid. This equation only valid if the pipe is horizontal. So what's the difference between the two? P sub z is piezometric pressure. And this piezometric pressure is something that we have talked about already in class. And piezometric pressure, P sub z, is the pressure plus gamma times z. And we talked about piezometric pressure when we were considering in a tank between two locations that the piezometric pressure was constant, because we'd say there's some z datum where it doesn't matter where we put the datum, but we're measuring elevation relative to the same point. There's a change in elevation, but as you lose z between 1 and 2, you gain pressure. And so in a static fluid where the water isn't moving anywhere, piezometric pressure is constant. What this equation is saying is that between 1 and 2, the change in piezometric pressure is what's measured by the differential manometer. The differential manometer, by subtracting the difference between the manometer liquid unit weights and multiplying it by delta H, you can find out the difference in piezometric pressure. And the significance of that, I think, will become clear as we work this next example. Before we hop into the example, any questions so far about what I mean by P sub z? P sub z, piezometric pressure. Yeah. So if we are going to apply this equation to here, what it says is, all right, at 1, consider not only the pressure at 1, but consider its elevation above some datum and the fluid involved. And so the reason why this equation simplifies to that one is that 1 and 2 have the same elevation. You know, this equation, if we expanded it out, what it says is that P1 plus gamma Z1 minus P2 plus gamma Z2 is equal to delta H gamma M minus gamma F. So for a horizontal pipe, the elevation of 1 and 2 are equal. So this term cancels out. So all we're left with is delta P, that is P1 minus P2, is equal to delta H times the difference in the unit weights. But the pipe's not always horizontal, as is the case in this example. The pipe is not horizontal. So there's a difference in pressure between 1 and 2. Look at location 1 and location 2. The pressure is different between those two locations for two reasons. There's two things causing the change in pressure. What was causing the change in pressure in this case where it was a horizontal pipe? The flow of water. The flow of water combined with the effects of pipe friction. You know, what was causing the change in pressure between 1 and 2 in this horizontal pipe is frictional losses. Energy loss due to pipe friction. So in this one, it's partly that. That's one of the two reasons that the pressure between 1 and 2 are different. And so what's the other reason that the pressure is different between 1 and 2? Elevation difference, right. So it's sort of like the hydrostatic. You know, we've got 1 and 2. Of course the pressure is going to be different because they're at different elevations. And so we're applying the hydrostatic equation between 1 and 2. So it's partly frictional losses and partly because of just hydrostatics. So what we're going to do in this example is we're going to apply the piezometric pressure definition to find out, first of all, what is the pressure at 2 and what's the change in piezometric pressure. All right. Now, to find the pressure at 2, I'm going to be applying the hydrostatic equation through the manometer itself. And the reason why is that inside the manometer, conditions are static. It's very, very important for you to understand how things are different in different locations here. First of all, in the pipe, water's moving. You can't apply the hydrostatic equation when the water's moving. There's different equations you should use when the water's moving. Hydrostatic means water not moving, right? Hydrostatic equation. But inside of this tube, it's in equilibrium. The conditions have settled down. There is a deflection, of course, but there isn't water flowing through this, the differential manometer. So since conditions are static, we can apply the hydrostatic equation through this tube. And that's exactly what I'm going to be writing on the board here, is the hydrostatic equation between 1 and 2 through the tube. So trace a route. You know, you could take your pencil and trace a route. How do you get from 1 to 2 through the differential manometer instead of through the pipe itself? It starts off with, you've got P1, whatever the pressure is at 1, plus, now we're going plus because we're going down through whatever the fluid is, so gamma F. In this case, the fluid isn't defined, but we won't need to know it, as you'll see in a minute when we combine terms together. And the distance that we're going down to get from 1 to this interface, the distance is delta y plus delta h. Nope. Oh, you're talking about the little bit that's right here? Yeah, kinda. But what we do is we assume that the diameter of that pipe is so small that essentially the pressure at the center of the pipe and the pressure in the manometer tube are equivalent. So we're just we're going to neglect the fact that it's flowing here, and we're not supposed to apply the hydrostatic equation when it's flowing.
And so what's your equation right here for? Where are we starting?
At
No,
1.
on the board.
Okay. We're starting at 1, pressure at 1, so at the center of the pipe, and now we're going down. So we're going to go to this interface there. So it's gamma F times delta Y plus delta H. So now what we're at, the location we're at is right here at that interface. Okay. And now we're going to go up to the next interface. So I'm just going to not bother to write that it's equal here and here. I'm just going to go directly from here, jump to that because it's equal, and now subtract the pressure to get me at that interface. So minus delta M times delta H, gamma M times delta H. And now I still have to go up a little bit further. I've got to get up to 2, and that is going to be going through whatever the fluid is. And the distance that I'm going to go up is delta Y plus Z2 minus Z1. Okay, is equal to P2. So what I did is I was here, and then I'm going up. The distance is delta Y, and then this vertical elevation difference between 2 and 1, Z2 minus Z1, is some distance. And then once I get up to there, that is equal to the pressure of 2. Okay, so just to summarize, I start at 1, go down through a fluid, sideways it's the same, go up, the pressure is decreasing, go up again, the pressure is decreasing more. I've got some common terms that I can cancel out once I expand this, and I'll illustrate that. This works out to P1 plus gamma F times delta Y plus gamma F times delta H minus gamma M delta H minus gamma F delta Y minus gamma F Z2 plus gamma F Z1 is equal to P2. So I'm just expanding out each of the 3 terms. And what you'll see is that here is gamma F delta Y. I can cancel that out because there was plus gamma F delta Y, and here's minus gamma F delta Y. All right, so now let's just substitute in the actual values, the actual pressures that are known. Over here on the right, it says that the pressure at 1 is 450 kPa. So here, 450,000 newtons per meter squared, plus gamma F times delta H. Now the F in question, it's water that's flowing through the pipe, and the manometer fluid is mercury. So through 9810 newtons per meter cubed, and the delta H that's given, the deflection says 5 centimeters, so that is 0.05 meters. Okay, now minus gamma M, so that's 133,000 newtons per meter cubed times the delta H, which is 5.05 meters. Now minus gamma F times Z2. Now we don't actually know the elevation of Z2, but we do know that the difference between Z1 and Z2 is 1. So since delta Z is 1, I'm going to say let's let Z2 equal 1 meter and Z1 equals 0. just by definition.
Any question?
Yeah.
Again, in your first line up there, delta, or gamma F times, yeah, that right there. We just call that delta Z instead of Z2.
Sure. Yeah, we could call it delta Z. Let's do. All right, so then it'll be 9810 newtons per meter cubed times 1 meter is equal to P2. Does everybody see what I did at his suggestion? Rather than saying let Z1 equal 0 and Z2 equal 1, we'll just write it in terms of delta Z. Okay, well, we've got, so this is 450,000 newtons per meter squared plus 490.5 newtons per meter squared. I like doing things in little baby steps. I make mistakes if I combine too many steps all together all at once. And paper's cheap. Mistakes are expensive. Paper's cheap. So, I'll just do it one little step at a time. Minus 6650 newtons per meter squared minus 9810 newtons per meter squared is equal to P2. Now, I think that this is a pretty good way to have it broken down right now, because it tells us the pressure at 2, like this line tells a story. The pressure at 2 is the pressure at 1, and then taking into account this term, this is one thing, the effects of one thing, and this is the effects of something else. Remember, we talked about why is the pressure at 2 lower than the pressure at 1? And we said there was 2 reasons why the pressure is lower. One of the reasons that the pressure is lower is because of elevation difference. And then the other reason why the pressure is lower is because of pipe friction. And these are the 2 different terms that correspond to those different factors. Just based on the hydrostatic equation, we know if it's 1 meter difference, 9810 newtons per meter squared, this is how much the pressure is different because location 2 is higher than 1 was. And then this term is measuring the pipe friction component. And so the piezometer itself, the differential manometer, this deflection is due to the pipe friction. And think about, what if the water stopped moving through the pipe? It's moving right now. If it stopped moving, what would happen to that delta H? It would go back to completely level. Just because of the elevation change, just having an inclined pipe would not have any delta H. That wouldn't cause a delta H. The delta H is because of the moving fluid and because of the frictional losses, right? So we'll finish the actual numeric part of this, and we find that the P2 is 434,030.5 newtons per meter squared. So that is the pressure at 2. Now, what is the change in piezometric pressure is the second thing that this example asks. Or in other words, what's the pressure change that's measured by that manometer? So what is the delta P sub Z? And we know from the previous slide that that is delta H times gamma of the manometer fluid minus gamma of the other fluid. So delta PZ, that means pressure at 1 plus gamma Z1 minus the pressure at 2 plus gamma Z2 is equal to delta H gamma M minus gamma F. The delta H is 0.05 meters, and the difference in the unit weights is 133,000 newtons per meter cubed minus 9810 newtons per meter cubed for water. So the difference is 6159.5 newtons per meter squared. So that is this term here, the pipe friction part of why the pressure is lower. The change in piezometric pressure. The piezometric pressure change measures how much energy loss there was due to pipe friction. Any questions? If it was a pipe was made out of glass or PVC, those are very smooth materials, and you don't have very much friction loss with a smooth pipe like that. And so there would probably be less deflection using a pipe or a PVC or a glass pipe than if it was made out of concrete or corrugated steel, something that's really rough. There'd be a larger delta H you'd see. So pipe type does change, yes. All right. Here is a picture of a weather balloon. And weather balloons are used to measure temperatures at really high elevations. It could be used to take measurements of atmospheric conditions or air quality at certain elevations. You probably heard about, the problems they were having with the ozone layer down in the southern hemisphere, where what were called carbonated fluorocarbons, CFCs, air conditioning fluids, would escape and would attack ozone in the atmosphere, which filters out ultraviolet radiation. So in the atmosphere, air is a gas, and gases are one of the fluids that we consider in fluid mechanics, and there is a typical change in pressure as you go up through the atmosphere. And this slope is called the lapse rate, the change in temperature with respect to elevation. And the change in pressure and temperature are very closely related. What this says is that if you go up through 1 kilometer of atmosphere, when you're in the troposphere, the temperature decreases by approximately 5.87 Kelvin per kilometer. The way that you can use that is you simply use the lapse rate, which is alpha. The slope of that line is alpha. And if you want to find the temperature at a certain elevation, you can use the temperature at the location that you know, whether it's atmospheric, at ground level, and the elevation at ground level and the temperature at ground level, and then you could use this lapse rate to find the temperature at a certain elevation. If you've ever been on a really long haul airplane flight, sometimes they have little navigation systems that says what your distance is to the destination and how long you've been flying and the temperature outside and the elevation, and it's very, very cold up there. If you're flying at 30,000 feet, then let's see, 30,000 feet would be about like 6 miles, which is about 10 kilometers. So if you're at 10 kilometers, then the temperature is negative 40 Celsius out there. So that'd be really cold to skydive out of an airplane that's going that fast, and it's really cold and windy. Now, this allows you to find the pressure at a certain elevation, and it accounts for not only the change in temperature, but also the gas law constant for air. So let's use this equation and calculate for the world's tallest building, for the Burj Khalifa. And let me dim the light so you can see that picture a little bit more clearly there. Let's say that on a moderately warm day in Dubai, the air temperature at the bottom is 30 degrees Celsius and the air pressure is 28.7 inches of mercury. The structure is 828 meters tall. So at the top, what's the air temperature and what's the air pressure? Oh, and that's Tom Cruise climbing on the Burj Khalifa. Did anybody see that movie? All right, that made it look pretty exciting, right? Okay. So let's go through and do the calculations and see what temperature it was for Tom Cruise. I think he does all his own stunts, and that was probably all 100% real. I don't think any of it was computer generated. He was actually out there. So the first thing that comes to mind is what was the air temperature and what was the pressure. All right, we'll do those calculations here. First of all, the temperature we have to convert into Kelvin. So the temperature at ground level is 30 degrees Celsius plus 273.15, puts it into 303.15 Kelvin. Let's say that the elevation at the base of the structure, the elevation I think is approximately 10 meters above sea level. It's pretty close to the sea, but not exactly at sea level. And we're going to put Z, the elevation aloft is 838 meters because the structure is 828 meters above the elevation of the base. So both of these elevations that are listed there are above sea level. If the pressure is given in terms of inches of mercury, 28.7 inches of mercury, then we have to multiply that by 25.4 millimeters per inch to get 728.98 millimeters of mercury. And we can convert that into atmospheres or into 760 millimeters of mercury per atmosphere, and then multiply that by 101.325 pascals per atmosphere. So converting from inches to millimeters, and then from millimeters of mercury into atmospheres, and from atmospheres into Pascal. So the pressure at the base of the structure is 97.189 pascals on this particular day in question. The temperature aloft will be the temperature at the base of the structure minus the lapse rate alpha times the difference in elevations. The temperature at the base was 303.15 Kelvin. Subtract the lapse rate 0.00587 Kelvin per meter, and then the difference in elevation is 828 meters. So the temperature aloft is 298.3 Kelvin. By the way, that is 25.14 degrees Celsius. So it is a little bit cooler up there, 5 degrees cooler. On a hot day like that, 5 degrees feels like a lot. All right, now what we're going to have to do to find the air pressure is work on the exponent constant on the previous page, and I'll write the equation here in a sec. Well, here's the question. Here's the equation. To find the pressure aloft, we start with the pressure at the base and multiply it by the following expression. Temperature minus alpha Z minus Z naught, temperature at the base, and it's to the power of G divided by alpha times R, where R is the gas law constant. For air, the R of air is 287 joules per kilogram Kelvin. We've seen that constant before. And the alpha that we already have used was 0.00587 Kelvin per meter. And G is 9.81 meters per second squared. Okay, so the pressure, they're asking what is the air pressure up there. Since they started by giving the air pressure as 28.7 inches of mercury, we could either put it in those terms or we could start with the pressure in pascals that we had at the base. Either one would be okay. Let's say if it was the 28.7 inches of mercury. And now what we're putting into the brackets is 298.3 is the temperature at the base minus the change. So the numerator of this expression is basically the temperature aloft, which we previously had calculated as 298.3 Kelvin, divided by the temperature at the base, 303.15 Kelvin, and then the ratio of 9.81 meters per second squared divided by 0.00587 kilograms, not kilograms, Kelvin per meter times the R was 287 kilograms meters squared second squared kilogram Kelvin. If we expand out the R, expand out joules, this is the units that we get. And so obviously the seconds are going to cancel, the kilograms are going to cancel, so the units do work out so that this entire expression here, and this was an exponent, so the ratio of the temperatures to the power of whatever that combined factor of, this combined factor here is 5.823. So it's the ratio of the temperatures to the power of 5.823, and that makes it 28.7 inches of mercury times 0.9091. So the atmospheric pressure up there has decreased by about 10% over that 823 meters of elevation. So that the final pressure is 26.09 inches of mercury. Or if we wanted it in terms of pascals, then we could just multiply 0.9091 by the pressure in pascals that we'd found previously. All right.
10 meters, where do you get that from?
Oh, that's just the elevation of the base of the structure.
That's a given, basically.
Yeah, that's a given. All right, looks like I've kept you 2 minutes over today, so I'll let you go 2 minutes early on Tuesday, because I want you to get that time back. If you've got any questions on the homework, feel free and stop by and let me know. Let's just take one last look at the announcements here. You've got homework 3A due on Tuesday the 17th, and then the lab 3 is due Tuesday in lab.